Hooray! Welcome to episode 145 of Quarkus Insights. We've been going for a long time. And so today we're talking about what's new in Hibernate Search, and we've got Yoann with us as a guest. But before we jump into Hibernate Search, I think we've got a couple of pieces of news, so we can do the news graphic just because it's there and we can.
We definitely do.
Yeah.
So, well, first of all, this is a busy week. We've done releases. We had 329, 352, and remember last week. If some of you remember, we had a CV in Gradle. We fixed that, but unfortunately, we also broke something, which we now fixed. So now it's hopefully out there. We have that 329 and 352. These are all kind of to fix these CVs. And then last week we had an impromptu session about LangChain for J, which is an extension we made to work with different various LLMs out there. So ChatGPT, Hugging Faces, and others. So there's on the YouTube channel, there's a whole us talking about that for 1.5 hours. You can go to there. But if you want to try LLMs now, there's a way to do it with Quarkus. And I don't even have my simple example in here. But if you ever wanted to do AI, do try that one out. And I think that's it has a newsletter, which you can get to. But it's been a busy week of various news. So no, that's the big thing.
Although us doing a release is barely news, really, because we do them so often.
That is true, but I wanted to highlight here that we are doing the LTS, the long term in the community. So the 32X is the one that we will keep updating for a while. 352 is the current previous release, which we also update if there's any major CV stuff coming out. But you'll see in next week, I think we're doing 3.6. Then we won't update 3.5 anymore, but we will continue to update 3.2. So that kind of thing is, and that's a newish thing we've been doing in the last couple of months. So just to remind people that we actually have an LTS community called 32X, and we are continuing the 3.5 or 3X series, and we'll continue to release often and fix often approach. Cool. But that's it. That was the main news for that one.
Cool. So I guess we can switch over to Yoann now.
Hey.
So shall we show your slides?
Yeah, we will.
You got your slides.
So, thanks for having me here. I guess.
Before you start, do you want to tell us who you are, where you came from, why you're here?
Where I was going. I guess you want to know that. So I'm Yoann Rodiere. That's how it's pronounced. Good luck. I'm a member of the Hibernate team. I've been working on Hibernate Search for, it's been a while now. 7 years, something like that. Team lead for a little bit less than that. And before that, I was working on business applications and using Hibernate Search. So it goes back a while. I'm mainly working on Hibernate Search as part of the Hibernate team. I'm also working on other projects, but mainly on the Quarkus side, working on the Hibernate ORM integration in Quarkus. Hibernate validator from time to time, and a few things here and there. But I'm supposed to work mainly on Hibernate Search at least. And I work for Red Hat, by the way. That's all there is to say, I guess. Before I go into what's new in Hibernate Search, maybe you want to know what is Hibernate Search, because I guess not everyone does. So we'll a few things about the context here. We're talking about Java applications that use Hibernate ORM, the object relational mapper, and the relational database. If you're doing Python, if you're doing MongoDB, you probably won't find much of this relevant, even though in the future we do plan on making Hibernate Search work without Hibernate ORM, but it's not yet available in Quarkus, so I won't go through that here. So the question is, if you are in this context, you have a Java application, a Quarkus application, hopefully, you're using Hibernate ORM to talk to a relational database, how do you search in text? So you can do this. You can do the like and e-like predicate, use the wildcards before and after a string that you're searching for, and I can show you how it goes in practice. I have a demo application. I'll show you how it goes with this strategy and then with Hibernate Search with the same model. So it's a simple model, the same one than in the last Quarkus Insights that we did, by the way, but I improved it a bit and updated it. So there's a t-shirt entity with a name. Each t-shirt has a few variants with a different color, different size, different price. And each t-shirt is part of a collection that has a year, a season, and a few keywords because there's a thematic for each season. All right, so that's quite simple. It's enough to demonstrate what we want to do. So I'll start by going to the right workspace. And I'll start my Quarkus application. Now, it will, of course, start dev services, which implies starting PostgreSQL in this case, and only PostgreSQL. Once I have that, I can start searching, calling my REST endpoint that, well, I didn't show you, but it's really basic. It's doing a query with panache and using the like operator with a wildcard before and after the term we're searching for. There's a bit of lower casing going on, but nothing much, nothing very complex. So I'll run curl repeatedly each time I type something. So I'll look for car, right? And I'll get the results from my sample dataset that I have in my application. And here I have results about cars, so that's great. I have also a result about Picard, which has nothing to do with the car, but it's still there because we are doing a substring search, which is not actually a word search, but that's the best we can do with like, so it's not great. There are also other problems like no relevance sort. Here I have a t-shirt which is really very much about cars, and it's still second in my list of results. I have no concept of sorting my hits by how relevant they are to the query, which will become a problem once I have millions of documents, because then I'm likely to get hundreds of results for each query I do, and then most people probably won't go past page 1 and they will just give up. So I want my most relevant results to be first when I do full text search. I can't here. Another problem, if I search for bike, I will find a t-shirt whose name contains bike. If I search for biking, I will find another t-shirt about biking. But those two queries are really about the same thing. I would like to get both hits in both queries, but I can't because I'm doing substring search. When I search for bike with an E, well, it's not a substring of biking, so no luck there. So really, there are downsides to the like strategy. You have false positives, false negatives. It's feature poor. You don't have relevant sort. Performance is limited as well. That's important because you can't slap an index on your column when you're doing a search like that with a wildcard at the beginning and the end of your search term. It will perform poorly when you have lots of rows in your database and lots of text. So of course there are solutions in relational databases. Some which are very advanced. There are also standards, but the standards don't cover much. So it's likely that if you go that route, you will have to rely on vendor-specific syntax. Since a lot of it is vendor-specific, well, standards like JPA can't do much about integrating with it. JPA integrates with the SQL standard, and the SQL standard is not much. And actually, the current version of the JPA spec doesn't even cover what's in the SQL standard, which is, I think, the contains SQL function. Fortunately, Hibernate ORM does cover that, but still, that's not much. Feature-wise, like I said, some databases like PostgreSQL are quite advanced. They provide a lot. But still, those are relational databases. Full text search is not their focus, and that's fair. It shouldn't be, because then they cannot focus on everything, right? Relational joins and and having a basic coverage for every data related need out there is already a lot of work. So that's fine, really. They cannot reach the same feature coverage than dedicated solutions. Dedicated solutions like Elasticsearch, OpenSearch, or Lucene. Those are probably better candidates if you want to do full text search. So just to give you an idea, Lucene is a Java library that provides full text indexing of text with the goal of doing full text search, and it provides ways to actually execute your full text queries to do the full text search based on those indexes. Elasticsearch is built on top of Lucene and provides a fully integrated solution that you can start as a container, for example, and exposes indexing and search services through a REST API. And it can be distributed critically, so that you can start multiple Elasticsearch nodes and they will work as a cluster. OpenSearch is a fork of Elasticsearch that was created for licensing reasons, mainly since Elasticsearch, at least according to the open source initiative, stopped being open source by switching to the SSPL license, the same as MongoDB, some versions ago. So it stopped being open source, so OpenSearch was created, the fork, to provide
License drama.
a lot of drama in this case. So I'm mentioning both because even though OpenSearch is a fork, it's still very similar, at least for the basic needs. Most APIs that were there just before the license switch are there in OpenSearch, and it's only now starting to diverge because of the new features like vector search that are being added, and everyone is using its own API.
So are we supporting both?
Yeah, I will show you that.
Okay.
We're supporting both, and it's super easy to switch. I can talk more about how full text search work. Not sure if that's important or if I should skip it.
Okay, give the high level understanding
High
of it.
level,
Okay.
there's an inverted index called inverted because we go from content to keys, from values to keys, rather than from keys to values. So we basically have a data structure that gives us the most the most efficient possible lookups to get the results we want. Because what we want is to look for a few words, a few tokens, and to get the list of documents that contain those words, right? And the inverted index is that. There's a bit more information like the positions of tokens in the document and so on to provide advanced features, and there's also a lot of optimizations that make it super hard to understand if you look at the binaries, but in principle, it's that simple. Of course, if we want to use that data structure, if we want to use it efficiently, we need to perform exact matches. So that could prove a problem. If you have things like a user searching for car uppercase and it's in lowercase in your index, you start having problems. So we want to pre-process our text before indexing it and before querying. So we have this concept called analysis in the Lucene world. It's about first tokenizing our input, so turning a chunk of text into a stream of tokens, and normalizing it, like for example applying a lowercase filter to put everything in lowercase, like also removing what we call stop words that would match everything, like a. In English, if you look for a, it will probably appear in every single document, so it will just kill your performance, and also won't bring anything. Maybe it will make processing more complicated for no reason. So there are optimizations that are included in analysis, like the stop words filter. And there are things that are more about making sure that tokens that are different but really mean the same thing are represented with the same string of characters in the index and in the query. Like for example, driving. If you have a query that says they drive cars, you want drive to be represented with the same string than driving, so that you can perform an exact match from the tokens provided by the users when querying against the index, against what was indexed.
You got a question about, like, does this analysis work in language other than English, or is it worse than English?
So all this analysis is fully configurable. I'm showing you here a tokenizer. It's a white space tokenizer, a lowercase filter, stopwords filter, stemmer. That's a completely arbitrary chain of filters. I can fully configure that, and there are dedicated filters for each language. For example, the stemmer, it has to be aware of what your language is, otherwise it won't do anything relevant. So there's a stemmer for English, there's one for French, Russian, Korean, whatever. Well, not maybe not every language, but Lucene has support for many languages. I know there is also support for analysis of Japanese kanjis, stuff like that. I can't write it or even read it, so I couldn't tell you how it works, but I know the feature is there. The point is, you have a default analyzer available in your solution, but you will maybe not need, but probably want to customize it to get the best out of it. Because analysis is really what will make your search shine. So yes, in summary, when we put it all together, we have a document ID and raw text, we analyze it, we get a document ID and tokens, we put that in an inverted index, and when we query, well, same thing really. We have a raw text query, we analyze it, we get tokens, we pass that to the search engine, which will look up those tokens in the inverted index and spit out a list of matching document IDs. That's the general principle. There are lots of complicated research behind it, in particular to give you a relevance sort, like how to make sure those document IDs are ordered from the most relevant to the least relevant. Well, it's a math formula, basically. I won't go into details. What's important is to know that it's there, it's complicated, but we don't need to know what it does exactly. So where does Hibernate Search come into play? Well, you have your data in your database and you access it with Hibernate ORM, which is great. That works. That covers lots of use cases. You have transactions, you have joins, and you're happy with it. Now, in order to perform full text search in the Lucene world, you will need to move that data to Elasticsearch. And hopefully, you will keep it updated. It's not just a one-time thing, because your data will change over time. So you will need something to synchronize that, to integrate those two, and that's what Hibernate Search is about. One of the main problems it handles is denormalization. Because in your database, everything is normalized. You have a table for your books, a table for your authors, and you won't duplicate the data about one author just because he authored multiple books, right? You will just have references, foreign keys, and all the stuff. Now, that's great, and it must stay that way, that's for sure. But in Elasticsearch, you don't have that. You don't have joins. That's just not how it works. It's a document store. So the idea is that in Elasticsearch, you will need to denormalize your stuff. But then, so that means if you have an author that authored multiple books, you will copy the data to every book so that you can search for books by author name. But then, what if the author gets renamed? So that's a bit of an artificial example, because that wouldn't happen that often in real life, but with many data types, just updating a column is business as usual. So what happens if you rename your author? You will need to reindex both books. What if you have 2, 3, 4 levels of indirections? Then it gets mighty complicated to update all this stuff and to keep track of what you need to reindex every time you updated something else. And that's where Hibernate Search helps. You will annotate your domain model, and Hibernate Search will deduce which changes require reindexing what, and it will automate this process. So yeah, I'll answer the question right now. I don't know if it hasn't been asked, but it often gets asked. You could do this by yourself, but it's really hard once your domain model becomes complicated. And yeah, maybe you store the death date, and then that's the kind of thing that you update. Generally, just once, though. So how it works is Hibernate Search actually registers listeners info Hibernate ORM, so that when the application requests an entity change, ORM will send the SQL to the database, of course, but it will also send a change event in Hibernate Search. Hibernate Search will store this event in the session. On pre-commit, ORM will send another event to Hibernate Search, which will then process these events, load the necessary data, because if your application was just changing the name of an author, it might not have all the books loaded in memory, but we will need to load them in order to reindex them. So it will load what's necessary and then build the documents, the relevant documents, so that after commit, it will be able to send the documents to Elasticsearch to reindex them. Why after commit? It's because of rollbacks. You don't want to have indexed something in Elasticsearch, then get a rollback and need to compensate the changes you made. So that's why Hibernate Search does it after commit.
Just looking at this diagram, I think you've already totally answered why you wouldn't do this yourself and why you wouldn't roll your own, because there's a lot of moving parts.
There is. So I'll get to another diagram later that improves things, but also makes things more complicated. So yeah. Just so there's much more than this indexing stuff. Hibernate Search also provides a search DSL, and with many features, geospatial search, projection mapping, faceting, but it's probably better if I show you. So I'll get back to my workspace. I had a basic application that just used Hibernate Search, Hibernate ORM, sorry, and I have another one that uses Hibernate Search this time. We add another extension. It's Hibernate Search with Hibernate ORM and Elasticsearch. That's all you need to add as a dependency, but you will need lots of configuration this line. That's it. The rest is about configuring the data source and Hibernate ORM. So hopefully you already have that. There's something about logging, so you don't care here. This is for tests. But first, this is the only mandatory configuration you will need. We need to know which version of Elasticsearch we're talking to, because the different versions expose different APIs, sometimes even differences in the schema. Elasticsearch does have a schema. So in order for Hibernate Search to adapt, we need to know which version you want to target. And that's about it.
Yeah,
This
version here, you mean the remote server, right?
The version of the remote server. The version of the client is not very relevant because we're using a low-level client. It's basically a glorified HTTP client. So there's not much knowledge of Elasticsearch that could change over versions in the client. And this other one is something you'll probably see a lot in many Hibernate Search applications. It's about making sure that when we do the post-commit stuff that indexes your documents in Elasticsearch, we ask Hibernate Search to make this synchronous, so that when we get back from the transaction, when the thread that started and committed the transaction returns control and moves on to the next things it has to execute, we have a guarantee that all the changes are visible when you do full text search. That's important because Elasticsearch itself does not give you such a guarantee. You index stuff, it's indexed basically asynchronously, it's refreshed every second. It's an optimization. There's just a transaction log in Elasticsearch, and it gets applied regularly. So for tests, you probably want your assertion to be executed only when the changes are actually known to be applied. So this helps. Now, that wasn't a lot of configuration, but where it gets interesting is how you annotate your model. So you will annotate your entity with index to tell Hibernate Search to index that entity, but by default, it will index an empty document. So you will annotate also your properties and tell Hibernate Search, I want to map this property to that field. And I said that field, but it's more those fields, because you won't be simply mapping it to another property in a different data store. You will be mapping it to indexes, and those indexes have more options than just the data type. You will need different analysis, maybe for different use cases. You will need to enable things like projections. Maybe you want to be able to project on your data, maybe you don't. You will need to configure, you may need to configure lots of things. So you can map a single property to multiple fields in your Elasticsearch index. And you have multiple types of fields as well. So you have full text field, but you also have generic fields that you can apply to numeric columns, numeric properties. For example, you can have many things. So there are multiple types of fields, and you will have a different annotation depending on your needs with different configuration options. None of them are mandatory, by the way. If you want to just test the basics, you can just do this. But in a real application, you will probably want to refine your needs, your requirements. And when I was talking about denormalization, this is what triggers it. You have a t-shirt with a few variants. You will ask Hibernate Search to embed those variants in the index of your t-shirt. And it will do so. And you will know that when a t-shirt variant gets changed, it needs to update the t-shirt. Now here it's a bit cheating because it's an element collection. Basically, it's part of the same entity, but same goes for the collection, which is a separate entity. When you update your collection, Hibernate Search knows it needs to retrieve the corresponding t-shirts and reindex them. What does it index in each embedded entity, you will ask? Well, same principle. You will annotate the properties of your embedded entities as well, and that's what will get embedded. And in some cases, you might encounter, you might have entities that are embedded in multiple other entities, so you have access to filters to control exactly what you embed and where you embed it. That's about it. There's maybe one more thing. I was talking about analysis and how to configure it. Hibernate Search does provide a way to a DSL to configure analysis. You just have to implement this interface. annotate it. This is a Quarkus annotation that simplifies configuration. So you have a way to map your configuration to a specific persistence unit, backend, or index. But here we will just apply it to everything. Every index will have this configuration. And depending on your needs, you will configure a different analyzer. You will name it, then assign a tokenizer, different filters, and this will be part of the schema that Hibernate Search creates in Elasticsearch. By default, that's done on startup, but you can trigger it manually as well. Now, how does it work? How well does it work? Well, we'll have a look. Like with the previous application, Quarkus will start dev services. This time it has to start Elasticsearch, which is a bit less optimized on startup than PostgreSQL. PostgreSQL is blazing fast, like it takes milliseconds to start. But still, that's something you will only do once, because with Quarkus live coding, you don't have to restart your containers and application every time you change something. It gets updated in the background. So now I started my application. I will have a look at the dev UI maybe. Sorry. So if I go to localhost, here I have some echo. Yeah. So I have my Hibernate Search and the Elasticsearch extension. So there's nothing much in here. You just have a list of entities that are indexed, and you can reindex them. So I've done that. That's great. And I can just so here it's super fast, of course, because I only have a few entities. In practice, it can be much longer if you have thousands, millions of entities to reindex. It's a real batch process, and Hibernate Search also provides ways to do that with a what is called the mass indexer. If you have pre-existing data that you need to index, you have ways to do that in an efficient way and in a way that you can tune for best performance. I'll show you also the endpoint I have. So I have basic CRUD endpoints in my application, and I can do a search. If I do the same search as before, I'll ask for brief output. I don't want all the variants and all that stuff in the output. If I search for car, I get only two here. I don't have car.
Here, I don't have car. Can you zoom in a little bit, Yoann?
Sorry? Zoom in.
Just zoom in a little bit. Zoom in, yeah, it's small.
Here. Is it better? So I have the results without the unnecessary pcard because I'm working on words, on tokens, not on substrings. I also have a relevance sort. If I look for bike, same idea, really. I have stemming, so I will get matches on biking. And, well, it works great.
In the biking example, there was something about jumping over a log as well.
Yep.
Was that because it's sort of doing an association and it knows bikes jumping, or how does that come? Where does that come from? Or is that something else in the document?
In the results about bike.
Yeah. Oh, you queried for jump. I see.
No,
that would be
I
why
changed that.
Yeah.
But yes, you have a result. That's because of the fields I search on. If I show you, I show you the search service. Where is it? Here. So this is the Hibernate Search API. So I inject a search session into my bean. So that's a Quarkus feature as well. And I start the search on the t-shirt entity, and I give my predicate. In this case, I run a simple query string predicate. That's a predicate with a simple syntax for and, or, and various things that can be useful to end users. And I actually target multiple fields, some of which I wasn't showing you in the JSON output. So I think you had a match here on the collection keywords. There was a collection about bikes, and there's a bike jumping over a log, I guess. So that's why you had a match. And that's also interesting because it means you can search for multiple terms, and as soon as each term matches at least one of those fields, you will get a match, which is not something that easy to implement if you have just a like predicate. So at least it gets out of hand pretty quickly. So that's how it works. And yeah, I'm fetching with an offset and a limit to create pagination here. So this is the search API, and I can actually go further than that. I can, instead of, so that was great because I was fetching managed entities here. So using the results, I can actually benefit from lazy loading and batch association loading from Hibernate ORM because I'm working on a managed entity. So when I run this through my map struct to convert my entity to a DTO, I will benefit from everything Hibernate ORM has to offer. But in some cases, I might not need to load from the database. Maybe this will be a better example. I have an autocomplete endpoint. So the idea is to call this from a dropdown in the web UI. As people type, I want to update the list of results. So as you probably expect, this will be called a lot. I don't want to hit the database on every single query. So I select here. I call select to tell Hibernate Search what I want to get. And what I want to get is a DTO. It's a record that has a description of what I want to fetch directly from the index. In this case, so I just get the t-shirt ID in this case and the name of the t-shirt. So this is implicitly the name field extracted from the index, but if I wanted, I could configure it like this. This is equivalent. I could be a bit more exotic in my choices and fetch the collection name instead. I have full flexibility on what I will map to this, but here I'm just fetching the autocomplete, the ID and name, because that's all I need from my dropdown. So that's something new as well in Hibernate Search, in the new versions of Hibernate Search. This ability to annotate a class or a record with projection constructor and have Hibernate Search retrieve the corresponding fields from the index. Now,
so the feature is just that it works for records, right? Or
no. Previously, you had a DSL to configure your projections. So the feature is that it's there at all on classes as well as records. Before you just didn't have this annotation, and yeah, it's actually more complex than it looks. To implement, I mean, not to use. Among the projections that you might want, there's the highlight projection, which is also a new feature. The thing is, when you look for terms in your documents, you would like to present to your users what matched exactly. So in order to do that, there's a feature here. When you declare your projection, you can request a highlight projection on a specific field, and then you will get the result highlighted, which means we will add some HTML tags to the parts of the name that matched. I'll show you an example here. If I look for bike, for example, so that was only slow because I think I made some changes and I had to restart and reindex, but that's not the endpoint itself is fast. But what I get is this. So I look for bike and I get a highlight on biking. So it's not as simple as just as in adding the tags to the exact search term that I provided. It takes into account analysis, and that's why it's really useful to request Elasticsearch to do the highlighting. So yeah, that's one other feature, and maybe a more major one is sorry, I'll get to it. This, if I go to my properties here, I told you could put the Elasticsearch version. Well, if you want to do OpenSearch, you can say it. Say I want to use OpenSearch 2. That's something. And Quarkus, the Quarkus Hibernate Search extension will actually start OpenSearch instead of Elasticsearch. And also adapt, Hibernate Search will adapt to the differences, the increasingly numerous differences in APIs.
It deals with the license drama for you.
That's the idea. Yeah.
So before you go on with this, we've got a question about the highlighting, about whether it's configurable what you put as a highlight around the found terms, whether you use M or some other tag.
Yeah, it is. It actually is. I can show you. So if I go to my t-shirt service, I can, here I configure my highlighter. There are many configuration options that you can but do not have to use. One of them is I can put a span with a class. Let's say I want to put the HL class, and I want to end with a span here. And if I go to my endpoint, well, that's a restart, and I get this. So
cool.
You do what you want. You can choose the size of the highlighting you want, because on the name you probably want the full name. If you have a full content field, like hundreds of different sentences, you probably want a small snippet, and you can configure the size. You can ask Elasticsearch to return a full sentence, not just 50 characters, but you want the content from the beginning of the sentence to the end, taking into account the punctuation and all that. So it's pretty advanced, and you have a Java API to control it thanks to Hibernate Search.
Nice.
I think, yeah. One other feature that was asked a lot is the ability to, I switch to another application here, the ability to specify arbitrary JSON to integrate to your Elasticsearch schema. So the mapping and the settings. Those, you can do that now with the newer versions of Hibernate Search. You can specify a mapping file and a settings file that will get merged with the view that Hibernate Search has of your schema and will be sent to Elasticsearch when it creates the indexes. So you can customize a few things, like here the source field in Elasticsearch is basically the JSON of the original document. And if you're sending lots of data in there, you probably don't want it to be stored. So you can exclude it. And that can be done through a custom mapping JSON. That's one other new feature. We don't have much time to cover the last part, so I'll try to be fast. 1 second. Yeah, it's here. So last thing, the transactional outbox pattern. I don't know if you're aware, that's a well-known thing. I'm not inventing anything. This is from the Microsoft website. It's a well-known pattern that where instead of processing events directly in our business application, we will make our changes in the database and insert events in a dedicated table in our database as well as part of the same transaction. And we will have a processor in the background, a background worker that will process those events and do the work in the background. And we can actually apply that to Hibernate Search. Well, that's great. And it can be used for indexing. So instead of when you do an entity change, like usual, Hibernate ORM will do its stuff on the database. It will send a change event to Hibernate Search. Hibernate Search will store those events in the session, business as usual. But on pre-commit, instead of processing those events, we'll store them in the database. And then Hibernate ORM will commit for the events to be picked up later by an event processor running in the background and polling your database. It polls the database for events. When it finds one, it will select the data for the corresponding entity from the database, build the document, send the document to Elasticsearch, update the database to mark the event as consumed, so delete it, and commit. And this time it commits after indexing. Can you share the event processor between multiple microservices? Yes, you can. That's the beauty of it. I'll talk about this in the demo. So main advantage, there's no event loss. Either we push the changes to the entities to the database with the events, or we push nothing to the database. If we roll back the transaction, we roll back the events as well. So that's great because that means there's no longer the litter problem that you could have in rare cases with Hibernate Search, where you commit your transaction and right before Hibernate Search indexes your data, the JVM crashes. Then the event was in memory, so you lost your event. That's no longer possible because your event is stored, it's persisted. We also minimize latency because in your HTTP request processing thread, we will no longer fetch the data for additional entities. If you changed an author and we need to reindex books, we will not fetch the books in your HTTP request processing thread. We will do this in a different thread running in the background. That lowers latency, especially if you have a very complex model with very deep dependency trees. All we do is inserting a new row in a table, well, one per event. We also eliminate a small risk of conflict that we had before. When you have a book with two authors and you have two transactions in parallel updating this author, updating a different author, it's possible that your two threads will be sending a different version of the document in parallel, none of which is exactly up to date. They have a different change in them. And so whatever wins, you won't get an index in sync with your database. That was something that could happen rarely with the previous solution. Now that we are sending our events to the outbox table, we can actually make sure that one entity with a specific ID will always be consumed by the same, will always be indexed by the same event processor, and use sharding to assign part of the entities to each event processor. And if we do that, we know that we will never send two requests in parallel about the same entity to Elasticsearch. We will not send two updates in parallel, and we will not have conflicts. So to answer the earlier question, you can have multiple event processors. You can also have applications that don't have an event processor. The event processor always runs inside the application, but it's disconnected because it creates its own JPA entity managers or Hibernate ORM sessions and its own transactions, and it pulls the database in the background. And what you will you could have an instance of the application with an event processor, and none of the other instances will have one. Or you could have one event processor in each instance of your application. That's all configurable. One big advantage of this solution as well is you don't need an additional infrastructure. We're only relying on the database for the events. We don't require you to set up a JMS or a Kafka cluster or whatever. This is just for the specific need of Hibernate Search, and so you don't need to set up additional things that you wouldn't need otherwise. I don't know if we have time for the demo. Do we?
Well, we waited so long. Let's go.
Okay. So I'll just do it quick. First, the changes you need to your application. I have another demo here about outbox spotting. And so the model is a bit different, but that doesn't matter. Basically, what you need is in your POM an additional dependency for the outbox spotting coordination. And in your configuration, you need to opt in for outbox spotting. And as soon as you've done that, Hibernate Search will switch to this different strategy, will contribute to the Hibernate ORM metadata, these new event entities that it manipulates, so that if you export your schema with Hibernate ORM, the required tables will be included. And of course, you can customize their names and their schema and all sorts of things. So if I start my application, right, sorry, those are unrelated changes. So I'll just build my application, and then I'll start a compose file where I have one instance of my application that connects to PostgreSQL as well as Elasticsearch. So it has a bunch of information about dependencies, health checks. I have a second instance of my application. Sorry. I have PostgreSQL. I have Elasticsearch, one instance, two instances. So if I run podman compose up, hopefully this will start. And then, so I need to wait for the Elasticsearch cluster to form. Once it's fully formed, I start the application. And once that's done, it is, I can go to, yeah. So this is in prod mode. So I expose Swagger UI to the management interface. So it's a different port, something that can be useful if you have your own applications in production. I have a few endpoints to do CRUD on my entities. Here I have a few authors. I have Isaac Asimov. We'll try to rename Isaac Asimov, okay? Because we want to see what happens in the background when we do that. So I'll scroll a bit to remove the previous logs. So I'll tell my application that I want to rename Isaac Asimov to Blugerman because he decided to take his wife's name. And if I go back to my application, I see that a lot of things happened. So Hibernate Search processed one outbox event for the author entity with ID 5, and then another for the book, because when it processed the event for the author, it created an event for the book. So this was processed on the instance 2 of my application, but one of the books was processed by application 1 because this is all sharded. So we spread the load over all applications in my cluster. And as a result of the processing of the books, I see that requests were sent to Elasticsearch to reindex the corresponding books. And it all happens transparently. And if I actually start a new instance of my application that connects to the same database, sorry, over here, it connects to the same database, then it will actually join the same cluster of outbox event processors and rebalance so that we are no longer targeting the same part, the same shard of the of my database. I had two nodes before, so I had two shards spanning half the database each. Now I have three, and each will target a third of my database. And this is all fully dynamic because it's based on registrations that the application instances perform in the background. My point being, it's flexible, very flexible, but you don't need to configure anything because it happens automatically. And that's the beauty of it. Okay, we're out of time, so I guess I'll stop there. Just know that what's next, we'll work on integration with vector search in Elasticsearch and OpenSearch. We're working on that right now, so that you can possibly do sound search. You can do image search with Elasticsearch, provided you have the required model to transform your image, your sound, into a vector. And that's what you talked about last week, I think, about LangChain4j. Longer term, we'll offer Hibernate Search as a standalone, and maybe, if we get to it eventually, a Debezium integration. At least that's the goal. Okay, I'm done. Thank you for having me.
Yeah, let me know if you still have the echo. So that's good. So when you say standalone Hibernate Search, that means that it can be used for other stuff than Hibernate and even other stuff than ORMs. So used in general for any kind of model applying, searching.
It still works on Pojos, but you don't need these your entities essentially don't need to be Hibernate ORM entities. You don't have a dependency to Hibernate ORM or JPA anymore. You define your entities independently. So those could be entities from a separate framework or a dedicated database client, NoSQL database client. You will have to handle the passing of events to Hibernate Search to tell Hibernate Search this entity changed and here are the properties that changed. But from there, Hibernate Search will be able to resolve the corresponding entities that need reindexing and will be able to trigger the reindexing.
And could it be something where, because like with LangChain, you're also doing these kind of analyzing and stemming and splitting up docs and thing. Could you use Hibernate Search in that flow? I'm just thinking out loud here.
I haven't looked very much at LangChain4j for now, so I couldn't say. But if it needs to basically manipulate entities and have them persistent into Elasticsearch, yes, Hibernate Search in standalone mode can definitely do that.
All right, interesting, cool. Okay, but that's got, and yeah, you got all the links here. We'll add them into the show notes, and yeah, and Jonathan, thanks for the questions, and thank you, Yoann, for doing the demo, and yeah, we'll see you next week when it comes around.
Thank you.
Thank you, and I'll find